My name is Dimitrios, and I'm engaged in computer security since 2002. The last couple of years, I focus on Android security. And about a year ago, I joined the Microsoft Defender Research Team as a senior security researcher. And I'm here to talk to you about how an Android application can drain your wallet. And the reason that I choose this category is due to the fact that it has a very unique and very interesting flow from a researcher's point of view. So before I go to the details on how this malware actually works, let me first go through some definitions that we're going to use in the next few slides. And let me first explain what is billing fraud. So by billing fraud, we refer to the malware category which contains code that can charge the user in an intentionally deceptive way. And we have a couple of subcategories of billing fraud. We have SMS fraud, call fraud, and toll fraud, with the last one being the most interesting one and the one that we're going to focus in this presentation. So when it comes to toll fraud, we're talking about a malware family with a multi-billion-dollar yearly estimated revenue, and one of the most prevalent Android malware categories according to the Google Play's transparency report. It is also very popular. I'm sure that most of you have heard about the Joker family, and this is due to the fact that it uses the Google Play Store as its main distribution mean. Another thing that I want to talk to you about is the WAP Billing Mechanism. So what is a WAP Billing Mechanism? It is a billing mechanism which uses the wireless application protocol in order to let the users purchase services, products online, and get charged directly in their phone bill. So here on the right side, I have an example of such a service which uses this mechanism. So as you see there, only customers are eligible for subscriber benefits. And when we're talking about customers, we're talking about users which are using a specific SIM operator. Another thing is that the customers can subscribe to a specific service by navigating to a WAP-enabled website. Then they're going to receive an SMS, which is going to inform them about the billing interval, the next billing date, and this type of info. And finally, the customers cannot subscribe to more than one service subscription package at a time. So let me summarize the steps so you have an idea of what is the overall process. So first of all, the user has to navigate to a WAP-enabled website, and by the time that the server is going to receive this request, you're going to send back a subscription page. So this subscription page usually contains a subscription button, so the user has to click, and by the time that the server is going to receive this request, a new request, it's going to send back a PIN, an OTP. So this is done either using an SMS or the HTTP protocol or even the USSD protocol in some rare cases. And the user has to send back this PIN to the server. The server will receive this PIN, will verify it, and finally send the SMS that I showed you in the previous slide, which informs about the billing date and all this kind of information. Now, please note that the steps 4 to 6 are not always there and depend on each implementation of the service provider. So what is now a fraudulent subscription? So by fraudulent, we refer to a subscription which takes place without the user's consent, without the user interaction, and actually without even being noticeable to the user. So the malware has to perform all these steps that you see here in order to achieve this type of subscription. So it has to make sure, first of all, that the device is operating in a mobile network. And this is done by either wait for the user to switch to a mobile network or force the device to switch to a mobile network. Then navigate to the subscription page, simulate the user's click on the subscription page, intercept the PIN which is sent from the server, send this PIN back to the server, and finally keep all this process silent in order not to be noticeable to the user. So let's see how these things are taking place now from the malware side. And before everything starts, before these steps start, one critical information that the malware has to retrieve is the SIM operator. So on which SIM operator the device is registered. So this type of information can be retrieved from a device by using the MCC or MNC codes and the specific API calls which I depict here. So either using the get SIM operator API call of the telephone manager or the get method of the system properties class with the difference between the two of them that the one can be invoked directly because by simply importing this specific class, while the second one has to be loaded using reflection because it's marked as a system API. Now on the lower side, I have an actual code of one of the latest Joker payloads, which, as you see, it checks if this information that retrieved from the device starts with 655. So this one actually belongs to the South Africa SIM operator. So if it starts with this 655, it will proceed to the next steps. And the next step is to make sure that the device operates on a mobile network. And how this is done. So wait for the user to switch to a mobile network. So create a connectivity manager instance. Then from this, perform this API call and get the network information out of there. See if the device is connected using a mobile network and go to the next step. Or the other way is to force the device to switch to a mobile network. And how this is done? So before SDK 29, there was a method there which is called set Wi-Fi enabled and allows an application to disable the Wi-Fi. So this, doing this, the device will switch automatically to a mobile network. And this, as I said, was before SDK 29 because in SDK 29 and after, we saw a new technique. So use the network request builder and define some specific capabilities there. Then use the connectivity manager in order to request this network, and finally bind the process to the network. And as before, I have an example of this technique on the right side, the demo code, which is more easy to understand. So create this network request builder, define the capabilities that we need. They actually want the device to be able to connect to the internet and use mobile connectivity. And finally, request this network from the connectivity manager. When this network is ready, bind the process to the network. So with this, in this way, they just make sure that the device operates on a mobile network. So now the next step is to get offers, to know where exactly to navigate. And this is done by communicating with the command and control server. The communication, of course, is either encrypted or they use some kind of encoding or even gunzip. And here again on the right side, you can see that the malware communicates with the command and control server, receives a JSON object which has some URLs, some offers. And one of these offers may lead to a redirection chain, which will finally end up on the landing page. So this landing page is a page which has the button that I described before, and it's going to be loaded in a web view, which is not going to be visible to the user. So far, the process remains silent. The user can't see anything. So now, a very important operating system, Android operating system component which this malware uses is an Android OS handler. So what this handler does is getting info about the current stage of the subscription process and acts according to the stage. So when the page is finished loading or when an SMS is received, the handler is going to receive a message and then is going to act somehow. So here's an actual code which shows exactly that, receives this message, depending on the what parameter of this message is going to perform some kind of an action. And one critical point, one critical phase of this process is when this page, the landing page, has been loaded. So what has to happen right now is that the user has to click on the subscription button. And this is done by using JavaScript. So the Android OS handler will inject code which is similar to this one that you see here, and it does something like the following. So it will scrap the page and search for elements which are clickable and they are relevant to the subscription process. For example, they're tagged like confirm, yes, click, enter, subscribe. And all these elements are going to be sent to a function which is called C, that as you see there. And this function is going to act in two steps. So the first step is to call another function which is called JDH, and this function will do the following. We'll check if a cookie has been set, if a specific cookie has been set. So if this cookie has been set, then it's going to set back false. If this cookie hasn't been set, then it's going to set this cookie and it's going to set back true. Now, what this cookie is doing, it's actually marking the page. So which means that the malware has already subscribed the user to the service. The user cannot subscribe to the same service more than one time. So ignore this page and move to the next one. And exactly that's what the initial function will do. Will either submit, click, or it will just pass the specific element and go to the next page, the next offer. So we have seen how it clicks now on the subscription button. What is next? Next, as I said before, the server will send back a PIN, will send back an OTP, and this OTP has to be read by the user and sent back to the server. So how the malware does that? Either using an SMS broadcast receiver, or binding the notification listener service, or using an SMS content observer. Now, the logic between all these techniques is about the same. So using the first technique, just declare the required permissions in order to do that. Create a class which extends the broadcast receiver, and in the receive callback, check the body of the message if it contains a specific keyword. Then extract what is after, I mean the PIN, and submit it back to the server. Now the submission can be either in the same page using HTTP protocol, or even using an SMS. For example, using the send SMS text message. The other way is by extending the notification listener service. And again, the logic is the same. Like I said, is about the same, but the implementation is different. Create a class which extends the notification listener service. And in the notification posted callback, just check the body of the notification. If it contains a specific keyword, extract the message and send it back to the service provider. Finally, another way is by using Content Observer, which what the Content Observer does is receiving callbacks for changes to a specific content. What we care about, what malware cares about here is about the SMS content. So if some changes happen there, it's going to get trigger the unchanged callback there, and will perform exactly the same steps, which is check if there is a specific keyword and send the PIN back to the server. Last but not least, keep everything silent. So all this process that you saw so far has to be not noticeable to the user. So since SDK 18, an application which extends the notification listener service can cancel the notifications of other apps. What this means is that your SMS application can simply be cancelled. The notification that you're receiving your device can simply be cancelled, but by an application which extends the specific service. And this can be done by using one of these API calls, for example, cancel all notifications to cancel all the notifications, or a specific one using a specific key, or an array of notification using an array of keys. Another way of doing that is by using the abort broadcast in the broadcast receiver implementation that I showed you before. All right, so let me summarize what we have so far, all the steps that we have so far. So we said we have a WAP billing mechanism which can be used to enable the users to purchase products and services online and get charged directly to their phone bill, right? Then we have the subscription process, which requires from the user to take some steps in order for it to be valid. Then we have the toll fraud from the other side, malware, which performs these steps in order to simulate the user interaction with the service and perform what we call a fraudulent subscription. And these steps, as I said before, include navigate to the WAP-enabled website, simulate the user clicks, intercept the OTP and send it back to the server, and finally keep all this process silent. All right. So you might now think that we have a malware which actually is its behavior is very complicated. It uses a lot of API calls, a lot of permissions, so it can't be that hard to detect this type of malware. The behavior is very characteristic. You can create very, very specific signatures in order to detect it. So the answer is actually here is that it is very hard to detect this type of malware. And why it is very hard to detect? Because it uses a lot of detection evasion techniques. And It uses, for example, steganography in order to hide the payload in seemingly bending files like JPEG files or PNG files or even the assets folder. Cryptography, each sample has different key for, let's say, its main operating strings. Obfuscation in order to evade the static type signatures. Dynamic code loading, simply said, the code is not there. What you saw so far is not in the initial APK itself. It simply gets downloaded and executed. And finally, you have clocking. So the malware has to make sure that certain conditions apply in order to perform these steps. Dates, a SIM operator, is the SIM operator targeted, or does the application runs in some kind of a VM or something? So all these in combination are used for from the malware in order to evade detection. And I have a showcase here. I have one of the latest Joker malwares that we traced recently. So this actually is an SMS application which was published in Google Play. And what is the first step? What it's doing as a first step is just check if it's still published or it got published in the Google Play. So send an HTTP request to the Play Store, see if we are published, and then proceed to the first stage. So the first stage is to check the assets folder for a specific file, if this file is there. So make sure that if we find the file which ends with 355, then we're going to the next step. And please notice that in the first versions of this APK, this file was not there. It was not weaponized. It was clean. So later, this file was added there. And when this file was found, use AES in order to decrypt it. The key was hard-coded in the DEX file. Use this key in order to decrypt the file. And the dropped file, which is going to be dropped actually in the data directory of the application, is actually an ELF file. It's a library. It's going to be loaded using the system.load. And the next step is to trigger a native function which is inside this initial payload. Now, we are moving to the stage 2, which takes place on the native layer. So here, all the strings that we have, of course, are encrypted, XORed, actually. And they are XORed back to the initial string by using a key which derives from the Java side. So decrypting the strings, we traced calls to the DEX class loader, to the load class, and actually to the name of the next payload, which we're going to see in the next stage. So when everything is there, when everything gets decrypted, the next step is to do the same process, but from the native layer. Now get, again, the assets folder and search for another payload. Now this payload is the one I show here, which ends with 300. And if this payload is there, XOR it in order to get a DEX file. So we're at stage 2, we XOR the file, and now we have a DEX file. So this DEX file is going to be loaded using the DEX class loader and the load class with a specific class as a parameter. And finally, perform a call, JNI call to the call static void method function in order to call a function which is on the Java side. So now we move again to the Java side. We have the third stage, which is the DEX file, which is I talked to you about before. So now this DEX file will communicate with a command and control server. This command and control server is hard-coded, as you see in the file itself. So it will communicate there. It will download another file, which file is a jar file. And it will load this file by using both Java reflection, actually, and the DEX class loader in order to load it. And finally, as the last step, this file will check if the SIM operator is compatible, is targeted, and start the steps that I show you in the first slides. All right, so to summarize this phase, what we have actually the initial APK, which is an SMS application that you might even download it from Google Play. It was thousands of installs regarding this app. And in the first stage, it's going simply to check if it is published, and then it's going to fetch a file from the assets directory. This file is an ELF file, and then it's going to proceed to the second stage, which is the ELF file that is going to check again the assets folder, fetch another file, which is a DEX file. This DEX file will communicate with a command and control server and download the jar file. And this jar file will do the final test, which is check if the SIM operator is targeted and do the actions that we show you before. All right. Now that we have a full overview of how it evades detection, how it performs this Tor fraud cycle, now let's see how it gets published in the Google place in the first place. So what the malware developers do is actually using what we call a penetration strategy. They want to penetrate the Google Play, the Play Store, in order to be able to publish these apps and get published as more as they can. So what they do is use open source applications that they belong to a very, very popular category. For example, camera apps, SMS apps, beauty editors, whatever you think. Apps in general that can take a lot of installs in very short time. And in the beginning, these apps are uploaded, are published and weaponized. So wait for these apps to get a specific threshold amount of installs, and then publish an update, create an update, which will contain the actual payload, the actual starting phase. So, and the last actually step here, as I mentioned here, actually, is that keep the process, keep the APK as clean as you can, right? So, as you saw, just as an asset file in order to start everything, and the rest can be downloaded and executed. Thankfully, that this type of strategy, this penetration strategy that I show you, creates what we call secondary signals. And what are those secondary signals? So you might see applications which have excessive permissions for what actually they're doing. So you have a camera app which requests you for an SMS receiver, or to read your SMS, or to bind the notification listener. In general, you have applications that what they're requesting doesn't make sense with their functionality, right? So the other thing is that they have common user interface characteristics. For example, they have common icons, policy pages, buttons, similar package names, developer profiles, and all this due to the fact that these apps are massive products. So there is an automated process which creates this type of apps. So you can understand that they have similar characteristics, a lot of similarities. Another thing, of course, is the user comments. Although, due to the fact that this malware is, like I said before, it's almost not perceivable from the user side, you can't rely on the comments in order to flag these secondary signals. All right, now let's see what chances we have from a detection side, from the detection point. And when we move to the client side, let's say the application that you have installed in your device, I'll be honest with you, we don't have many options here. And this is due to the fact that the Android operating system imposes serious restrictions on what one application can retrieve for another application. Each app is trapped in its own sandbox, and the information that can retrieve for another app is, let's say, strictly controlled from the operating system itself. So you can't do much here. What you can do is a simple static scan, again, which is based on signatures you're going to retrieve from the cloud, or use some kind of a VPN in order to monitor the HTTP, HTTPS communication and maintain some kind of a blacklist of command and control servers, and trigger some kind of an alarm when the device communicates with such a server. When we move, though, to the cloud side, there are a lot of things that we can do there. And what we are trying to achieve is have the best results using the less resources that we can. So this is a blueprint, actually. This is a raw blueprint of what we suggest. And it is a multi-phased process which starts with a steady feed. So this feed, imagine that we have apps, we have a pool of apps which can be fetched either from the Google Play Store or off-market, or even from the users or researchers. And during the first stage, during the first filtering, these apps are going to be filtered for the secondary signals that I talked to you about before. So check for similarities, for common icons, for excessive permissions, and this type of things. And the result is going to be either the app doesn't have anything, doesn't seem to have any kind of this type of signal, or it is suspicious, it has some signals, it reaches a specific, but it didn't reach a specific threshold, so it's going to rescant after the next X amount of time. And finally, suppose that it has a specific threshold of signals, then move to the next stage. Now, the next stage is a classic, let's say, a traditional static scan. So what we do, scan the manifest, scan for specific API calls or specific permissions or specific strings. And again, the result is going to be, as before, nothing due to the fact that it's missing a critical, let's say, API call or some kind of a permission that's not there. And or it has some, so it's going to be rescanned, or finally it reaches our threshold and is going to move to the next stage, which is the most demanding from, let's say, resources point of view. So what we're trying to achieve here is to trigger as much functionality as we can, so we want to expose this functionality as much as we can. We're trying to, let's say, interact in a clever way with the malware and at the same time observe some things. So what observe? Observe the HTTP, HTTPS communication of the malware, use binary instrumentation in order to log the API calls or even intercept these API calls. Remember I told you that it searches for specific SIM operators, so try to change the return value of these specific API calls and see how it reacts, or perform some type of memory dump the DEX files which might be loaded. This actually can be used in order also to bypass some type of protection, for example, packers, or even in some cases encryption. So check for dropped files in the data directory. If something has been downloaded or has been decrypted and dropped there, take this file. And finally, trace the JNI calls and, of course, dump the memory in the native space of the app. And the final result of this, the final, let's say, product of all this process is, of course, to create signatures. Now, these signatures might be behavioral signatures, which are more general and based on, let's say, API calls or permissions that I said before, can be more specific, and enrich our database, enrich our signature database in order to be able to detect this malware in earlier stages. So now, I would say like a final thought in regards to this type of malware is prevention. What do we mean by prevention? So why does this app have to be published in the first place, in the Google Play? Why an app, for example, has to be an app, a camera app, for example, or a beauty editor needs this type of permissions, and why the Google Play itself allows this application to use this type of permissions and get published in Google Play. So at this point, actually Google made huge steps. And since November 3rd, 2021, the developer needs to complete what we call a permission declaration form. So if your application is using some high-risk type of permissions, or permissions that they are using, might be used in order to fetch the user's private info, so the developer has to complete this declaration form. Despite that, we haven't seen so far we haven't seen any move when it comes to notification listener service that I talked to you about before, and actually is the one that remains right now and the one that we expect from Google to take action in the future. Yeah, and this was the last one. If there are any questions that you want to ask.
Does anybody have any question at this time? Okay. It would appear
I will
not.
be around.
Dimitrios will be around, and you'll be able to have access to presentation and the slides in due course on the activity website. So for now, Dimitrios, thank you very much.
Thank you very much. Yeah.